today was with our acids and bases and ultimately knowing the difference between strong and weak. So the strong ones you need to memorize. If they are not strong, then by definition they are weak. Okay? Or by definition within Chem 130 and all the other general chemistries. The next thing is how would we report this? So one thing we looked at was we could look at the equilibrium relationship and look at the size of that K value. The larger the K value, the more products, which means stronger the acid. Okay. The issue with that is that you're then looking at values that are usually in the orders of powers of 10, and that's confusing for people to deal with. Okay. So we want to shift out of a system that deals with powers of 10 because powers of 10 are confusing. Okay. We don't like doing calculations with those. So what we invented to try and help with that was a new system for monitoring concentration. So if we think about safety, it's really difficult to try to yell at someone about safety and tell them the concentration of the solution. Okay? 0.15 molar H+. That doesn't really mean a lot to anybody because they don't know what molar means. If we even broke that down into moles and liters, that also doesn't really help out. Okay? Those are numerics that we just can't deal with easily. So what scientists or safety people went through and did was converted that number into something that was a little bit more reasonable to deal with, that didn't have to deal with decimal points necessarily. We invented the pH. The whole point of the pH for a solution is a way of measuring the concentration or reporting the concentration for an acid solution or, for that matter, a basic solution, so that we can look at a simple number and say that is now potentially a dangerous solution. Okay? So it puts a big red flag on it. What is your range for pH? 1 to 14. Within most of the stuff that we work with, we're probably sitting within 1 and 10. Why would we pick a system that keeps our numbers between 1 and 10?
We have 10 fingers. We
have 10 fingers. Okay? We now have a way to kind of come up with a relationship that is easy enough for us to count out on our fingers. Okay? And if we really need to get up into that 10 to 14 range, we could use our toes. Okay? It sounds silly, but that's what we're doing. Okay, we've created a system that allows us to wrap our heads around a numerical value. Okay. Within that system, not all numbers are equal. So low and high numbers end up being bad. Okay, those are more dangerous. Low pHs tend to be marked as acids. High pHs are bases. Okay. Dead in the middle of that, pH 7, is the neutral pH, which won't affect you, okay, or would have a minimal effect on you based on acids and bases. Okay? So we have this 0 to 14 range, really convenient because it allows us to now report it, well, that solution's a pH 1. Oh, that's really strongly acidic, I should be more careful with it. That's a pH of 7, it's not strongly acidic, it's neutral, I don't have to stress about it as much. Right? The pH comes from the concentration. So it is related to the molarity. Okay? But we had to come up with some way to cause that shift. That shift is ultimately a logarithm, and in fact a negative logarithm. So if I want to determine the pH, really what we're saying is you would take the negative log of your hydrogen concentration, so the molarity. And that's it. You now have the pH. Depending on what we may do from there, we might look at different P somethings. So you may hear reference to a POH or a PK. Ultimately, all the P is referencing is the negative log. If I want to take a PK, I'm going to take the negative log of whatever the K value is. Okay? If I want a POH, I'm going to take the negative log of the concentration of OH. I could take the negative log of anything and call it P anything. The one that tends to be most useful is the pH, and that's what it's there for. The last kind of sort of big topic is our electrolytes, which is really a tie back to the lab. anything that when you add it to water completely ionizes becomes a strong electrolyte. So strong acids are strong acids because they completely turn into the ions. That makes them strong electrolytes. Okay? Why do we care about electrolytes? Well, they allow for the passage of electrons through that solution. This would be why you don't make toast in your shower. Okay? Because that's going to allow, the water will allow for the passage of electrons through the toaster, through the water, ultimately through you, okay, in its attempt to make toast. Okay? Electricity passing through you isn't the nicest process. Okay? If you haven't done it, I don't recommend it. Okay? It hurts, okay, to get electrocuted. Okay? So that's all an electrolyte is. It allows for the passage of electric current. So anything with ions will allow for the passage of electric current. So if we go through and look at a variety of substances, we would need to come up with some way to classify and decide, are they electrolytes or not? Well, sodium chloride, what do you think? Is that an electrolyte? How would we know it completely ionizes? One hint, what kind of bond is there between sodium and chloride? An ionic bond. In an ionic bond, would we think ions? Yeah. Okay. For it to count as something that dissociates in water, completely ionizes, it must dissolve in water. Is sodium chloride soluble in water? Yes. Based off of what? Solubility rules, exactly it. Okay. Sodium is a group 1 metal. All group 1 metals are soluble, so the phase here is aqueous. That means sodium chloride is an electrolyte, and in fact a strong electrolyte. Right? What about H2SO4? Well, what is H2SO4? It's an acid. Which acid was it? Strong or weak? It's one of the strong acids, okay, that theoretically you would memorize. Okay? Because we know it's a strong acid, what does that mean? It completely ionizes when it hits water, which then means it's now a strong electrolyte. Sodium hydroxide? What is that one? It's a base. Is it a strong base? Yes. How do we know it's a strong base? Because we memorized our strong acids and strong bases. Okay? In that list, anything with hydroxide bonded to a group 1 or group 2 metal is a strong base. Okay? What happens when we move to the next row? Calcium carbonate. Okay? Do we have an ionic bond? Yes. Metal, non-metal. So yes, there's an ionic bond. Does it ionize when it hits water? Meaning, does it dissolve? What would I need to look up? I would need to look at the solubility rules. And when I look up the solubility rules, it says carbonates are typically insoluble. Or sorry, soluble. Yeah, I think they're typically soluble. So we'd say, well, yes, it is. But we have to remember the typical. What's the exception to our carbonates being soluble? Calcium. Calcium carbonate is insoluble, meaning it doesn't dissolve, it's actually a solid. Why is that problematic? When I add it to water, it doesn't form ions, which means it's not a strong electrolyte. Right? Deciding what strength it is then becomes a whole separate issue, but it's ultimately not strong. Okay? Because everybody's level of weak versus non becomes questionable. Okay? How about iron hydroxide? Is it an ionic compound? Again, yes. How would I decide if it's soluble or not? Solubility rules, and when going to the solubility rules, again, I find it's not soluble. So it's going to match the calcium carbonate is not a strong electrolyte. Same deal with the silver bromide. Okay? So we're looking for that ionic compound or strong acid or strong base. Those end up being our red flags for electrolytes. What happens when we move to the bottom examples? What is different about those? What's that? Okay, so there's more atoms present. What else do you notice that's different about those? Organic, work with, continue that sentence because we've never actually stated what organic was. Non-metals. There's no metal present in these, which means they're not ionic. If they're not ionic, what would we expect? We would expect them to not make ions, which means not electrolytes. Okay? And that's it. That's all we really need to get out of it. Okay? Some of them will ionize to varying extents, but that extent is not something that you're responsible for in this class. That quantification really would come in second semester general chemistry, maybe even into OChem. Okay? So you're trying to look for those big patterns behind it and use those patterns to come to some kind of quick evaluation. Make sense? Okay. The exciting thing about this slide, it's the last one. Okay. So we are entirely done with Chem 130. Okay. Which gets us now to what you should be doing for preparation for the final. There are two files posted on Canvas. Okay. One, what is the name of this file? Where's my mouse? Is that actually showing up? It is. You're just not going to tell me what that is. Okay, fine. I'll go the other direction. Ah! Oh, there we go. That works. One file is final exam memory list. Okay. Remember, through the course of the semester, I've been asking you to not memorize things, and so I've been providing you content. Okay? That content for the final, you have to have memorized. Okay? So there is stuff that I've said you have to have memorized. Processes, those are things that I'm not going to include in this strict memory list. What I'm including in this list are things that I would have typically given you. Okay? For instance, your solubility rules. Okay? Your complex ions, I've added a couple extras on top of the ones that I told you to memorize already. Okay? Charges for your common elements. Okay? Some conversions. Okay? Your, what are they? The SI units. Okay? Some of those common conversions you are, you're responsible for. Okay? So you should go through and have that content memorized because you are expected to have it memorized. Okay? I told you to memorize it throughout the semester. Okay? So hopefully it's not that much extra work to go through and do that extra memorization. Okay? This is not an exclusive list. There are other things that were required to be memorized, but for the most part, this covers the kind of extra stuff that I didn't super require throughout the course of the semester. After that, what we've got is our practice final. Okay, so it says Chem 130 review, final exam. Okay. This would be your opportunity to decide what do you want me to look at. Okay. If you don't care, well, then that's, I guess, your call.
What will be on the front page of the final?
So what is on the front page of the final is a good question. I can show you that. I thought I had the final right there, or the cover page right there. But I do not have it directly handy. Okay, so let's pause the video recording. And then everything else has to be put away. Ideally, you'd have your cell phones turned off, okay, out of sight, that kind of fun stuff. Bubble in your Scantron appropriately. I don't think I've had any problems this semester, but if we real quickly looked at a Scantron, okay, This is also something I try to look for on the final. We've got like what our scantron looks like, right? Everybody get it? Okay. To correctly bubble in, we'll show it in red, this would be a bubbled in answer for A. Okay. Incorrect. Incorrect. Okay. Also incorrect. Okay. It also needs to be in pencil. Okay. I do go through and try and check for that again. Okay. If you don't do A, bubbled in like that, and I have to go through and fix how you've bubbled it, I will subtract points because that is part of the test, and you didn't complete the test appropriately. Okay. I think we're okay as far as the class goes. Okay. So we won't stress too much on that. You'll get 110 minutes, so it's an hour and 50 minutes to complete it, 7 to 8:50. When you're told to stop, you got to turn it in, and that's pretty much all you get. Okay? 65 questions. The practice exam has 68 because they wanted to give you a little bit more practice. Okay? The other thing that you will get is I will give you the periodic table that you've been using. Okay? So we can put it to you guys right now. Do you want that all put on one page, or is it okay to have it split across front and back? Split across? I'll split it across front and back then. So the exact same periodic table that you've been getting, and then the directions on the first page. That is it. Yep. Yep. So that's why I has put up the memory list. You have to have that memorized. Okay. One of the things that you can do if you're nervous about memorization, like you think you're going to forget the charge on silver. When you get the test, after you've written your name and you're told you're allowed to start, you could go to silver and write +1 on your periodic table. Right? You could write next to zinc +2, cadmium +2. Right? You could even go through and say the aluminum was +3. Not carbon you don't worry about. Everything under nitrogen's -3, -2, -1. Right? That doesn't take that much time, but it now puts some content down that you could potentially use later on in the exam. Okay? So I would recommend trying to do a last-second memorization and then purge that information onto the exam. Okay? Remember back in exam 1 we talked about trends? Okay? You could add arrows. Say bigger. So you know size. So if you see a size question, you've already got the answer drawn on. It's now just a question of interpreting your information. Right? So the same process for every other exam still applies to the final. Okay? So I would recommend that you purge that information fast so that you don't have to think about it when the question does show up. Okay? The content on the final is not necessarily in sequence. The very first question could be a limiting reactant question. Right? We've all struggled with limiting reactants. Don't spend any time on it. Right? Unless you're one of those people that knows it. That's fine if you know it. If you look at it and you're like, oh God, limiting reactants, you should immediately stop looking at that question and move to the next question. Right? The more time you spend on questions that you don't know, the less time you'll spend on questions you do know, and your exam score goes down. Okay? So move to the questions that you know first and foremost. Make sense? Other questions? Okay, so if there aren't any questions about the prep for the exam, oops. What we'll now move to would be from the practice exam. What question did you have? Just start scrolling.
was trying to do it. And
Atomic notation.
Yeah.
Okay. What do we get for our basic pattern for atomic notation? It's our symbol, and then we have two pieces of information included next to our symbol. We get something up here, and we get something down here. Okay. What were those things? Atomic mass and atomic number. We could sort of attempt to cheat and use the periodic table, because the periodic table puts the atomic mass where? On the bottom, and it puts the atomic number on top. Problem with that is the periodic table, for whatever dumb reason, does it backwards. Okay, it's actually not a dumb reason. We're organizing the periodic table according to our atomic number, so we want the number to show up first. Remember, our atomic notation isn't an organization in the periodic table. It's for nuclear chemists that want to see if it's radioactive. Our atom is radioactive if it has a massive nucleus, which means the first thing that they want to see, the mass. And then the number gets written underneath. What subatomic particles contribute to mass? Okay. Protons plus the neutrons. What things contribute to the atomic number? Just the protons. So if we go back to the question stated, I have 25 protons. Okay, I have 25 plus 30, 55. Okay. What determines the symbol? Where's the symbol come from? The atomic number. So I would use the periodic table, 25. The symbol is Mn. Now that I have that information, I go through and scan through my possible answers. So the first two are wrong. Okay. I've got manganese for the last three. 25's in the lower left, which is good for those two, so this one's wrong. 55 in the upper left, there's my answer. Make sense? Okay. So you have to remember the location of where those pieces are. If you look at the other choices, notice the other choices could easily be confused. Okay? What else do they throw in here just to mess with your head? The number of electrons. Okay? Remember, this is not atomic notation, this is nuclear notation. Okay? I know it's labeled as atomic notation, it is written for the nucleus. Are there any electrons in the nucleus? No, so I don't care about the electrons. They're only adding them to throw in another number that you could potentially add into this to mess with your answer. Make sense? Next question. 50. Okay. So if we go through and look at question 50, a quick scan through that question tells you what are you looking for. What kind of question are you being asked about? Liters in gas, which should suggest what? We want liters at the end, so that could help us out. Okay, liters in particular of oxygen gas, so I could write O2. Okay, because it is a gas, what could I potentially be using? Right, we could use the ideal gas law. I know gas does not have two S's. And law is spelled with an A. PV equals nRT. Right, that is one option. That is probably the option that nobody wants to use. Fair enough. The other option 1 mole of a gas equals 22.4 liters of that same gas. And it doesn't specify STP. Okay? So this is a crap question, because if we're looking at gases, we have to know that information. Okay? Because that information is not specified, this could be your opportunity to raise your hand and prove that you know that that's a crap question. Okay? Or you raise your hand and say, I don't know what's going on with this, I think I'm missing something. Okay? And that's when I would point out, yes, you're missing something. It is implied at STP. Okay? So if we know it's STP, then I can get away with the rule in purple. If it's not at STP, then I would have to do the blue one. Okay? But I'm not given temperature or pressure, which makes that extra difficult. This question, I would argue, then becomes really, really, really nasty, because one of our multiple choice answers is none of the above. I would argue if they were fishing for that kind of answer, none of the above is also a wrong answer. Because it's not that it's necessarily none of the above, it's literally that you can't solve it. So the answer shouldn't be none of the above, it's that it's impossible to solve. Okay? So all of that taken together, as an instructor observing the question, the intent was that this was supposed to be at STP. Okay. If we know that, we're now saying the purple is valid. How can we go through and solve? What are we starting with? Okay. Do we need to balance the equation?
Oh, it's balanced.
Okay. They claim that it's balanced. It's not a bad idea to check. Okay. If it's a situation where the equation ends up not being balanced, okay, that would be something you could fight for points back on, because you were told it was one thing and it wasn't. Okay. It is balanced, so we can ignore that. So now what can we do? What are we starting with? 3 liters of carbon dioxide. Okay. So cool. The measurement unit, liters, is the same, but the substance is different. Okay. So I would need to set up a conversion. Okay. Can I convert the substances directly? Mole to mole, I can convert the substances. Am I in moles? No. So I can't convert directly. I'm going to have to get that liters of CO2 converted into moles of CO2. How do I do that conversion? I literally wrote it up there, right? 1 mole is 22.4 liters. You're expected to know that. That could be one of the things that you immediately write and purge on your test, so that you can then go back and reference it when this question shows up, or a question like this shows up. We're now in moles of CO2. Do I want moles of CO2? No, what do I want? I want liters of O2. So I need to get rid of the moles of CO2 in an attempt to get into liters of O2. What can I convert to? I can use the mole-to-mole ratio, moles of O2. What's my mole-to-mole ratio? Where's that information found? In the balanced equation, what number shows up in front of moles of O2? 5. What number shows up in front of moles of CO2? 3. The moles of CO2 cancels. Now what? I want moles of O2 converted into liters of O2. Where do I find that conversion factor? That's the one that we defined at the beginning. 1 mole of O2 is 22.4 liters of O2. What happens in my conversions? The moles of O2 can cancel. I'd end with liters of O2. Now I can punch it into the calculator and go through and try and solve. Okay. Does anybody see something that could potentially simplify your calculation? 22.4 shows up in both the numerator and the denominator, so I could cancel those. 3 shows up in both the numerator and the denominator, so I could cancel those. What's 1 times 5? 5. Divided by 1? 5. Our answer is 5 liters. We didn't need a calculator at all. Right? Yes?
So couldn't we have just started with liters and converted it from liters to liters?
Yes and no. The reason we can convert from liters to liters is because we are at STP. Okay? And we're looking at ideal gases. If those things aren't valid, then no, you can't. Okay? Which is why I would argue you shouldn't be jumping to that conversion. It is a shortcut, and it is valid in this case. Okay? But the instant it becomes not valid, you end up solving for something incorrect. I would rather you have the method set up correctly, okay, without shortcutting it. Does the shortcut work in this case? Yes. Is your work graded for this exam? No. You could just guess 5 liters too. Okay? Kind of make sense? So again, I'm pushing process. Yes, they're shortcuts. If you find those shortcuts, you are welcome to take advantage of them. The problem is sometimes those shortcuts aren't valid. Okay? They'll be valid in one case, but not in another. Okay? So if you have the process fully outlined, you don't have to worry about shortcuts potentially getting in the way. That was because this was a bad question. It needed to say it. It needed to say STP. Okay? So you as a student may not be able to make that assumption. Okay? What you should deal with is what I wrote in blue and purple initially. Blue, PV equals nRT, or if it's at STP, I can jump to the purple simplification. Okay? Either case, I've got a problem. It doesn't say it's at STP, so I can't answer purple. Okay? I can't answer blue because it doesn't tell me the pressure or the temperature. Okay? So the question is now inherently a bad question because you don't have enough context to be able to answer that question appropriately. That's why you would have to raise your hand. Okay? This is also why you have instructors that, in theory, proofread these very carefully to make sure this kind of mistake doesn't happen. Okay? If it does happen, that's where it then kind of falls on you or one of your colleagues to call attention to bad test writing. Does that make sense? Okay. Other questions on that one?
So if this was on the test and it didn't say at STP, would you put none of the above?
I would not answer none of the above because, again, it's not that it's none of the above. It's with the information given, I can't determine what the answer is. None of the above says that one of those answers is not true. That's not valid. The answer is 5 liters. So saying none of the above doesn't work as an answer. It is impossible to determine this, okay, without STP. So none of the above also doesn't make sense as an answer choice. I know. We're walking a fine line. And when we talked about gases, this was one of the things I said you had to watch out for. Sometimes we specify it, sometimes not, and it's just implied within the statement. Because that's the only way you could solve it, is if it was. Right? Next question. So 44, what are the predicted products from neutralization reactions? Which brings up a good point as far as studying goes. You can look at this, oh, I totally know neutralization, I know how to balance this. Just because you know how to balance neutralization doesn't mean that's what you're going to see on the test. What you'd see on the test is predict the products from a reaction that you're required to be able to predict the products from. Neutralization happens to be one of those. What other reactions are you required to know how to predict the products on? Double replacements, single replacements, combustion. Okay? You're required to be able to predict those products. Okay, so don't go through and just say, well, I'm really good at this one question. You will not see this one question again. What you will see is some derivation of it. Okay? So, following neutralization reaction. So we'd go through and look at our basic structure. Okay, in fact, I'm going to erase, I may regret that later. Okay. When we go through and look at our start, what do we have? What are we starting with here? An acid. How do we know it's an acid? Hydrogen and it's aqueous, or aqueous. Okay? Which means I have H plus and NO3 minus. How about the next one? What do I have? I have a base composed of barium plus 2 and hydroxide. Okay. If I'm going to initiate a double replacement, I'm going to combine opposite terms. H plus needs to go with OH, NO3 needs to go with barium. The result being, end up with barium with nitrate, and then hydrogen with OH. That will be one of the answer choices. At least it should be. Okay? And it would also be wrong. Why? Once we've done the swap, we have to make sure that we've balanced those proper products. Not balancing the equation, balancing the product. What is the charge on barium? A plus 2. What is the charge on nitrate? Minus 1. That formula is not balanced. How would I balance it? I need 2 nitrates. Not NO32, NO3, 2, parentheses. What is the charge on hydrogen? A plus 1. The charge on hydroxide? Minus 1. Is that formula correct? Yes. More than likely, they won't write it as HOH. They would write it as H2O. With that extra information, we could now go through and look at our answer choices and see which of our answer choices matched that. Oops. Okay. So our barium with our nitrate, oh, barium, 2 nitrates, H2O, that must be the answer. Read carefully. That says nitrite, NO2, not NO3, so A is wrong. Okay? A is wrong. The next one doesn't have nitrite. The next one does have nitrite, 2 of them, and water. That looks pretty good. I got nitrite again. That's bad. Last one gives me the nitrate and 2, but now it just says H2. Okay? Where did the oxygen go? That one's wrong. So C ends up being the answer. Is that you, Bev?
Yes.
Does that make sense?
It's still not balanced.
What are the predicted products from the following neutralization reaction? Does it ask you to balance?
No.
No. So if you want to balance it, by all means, go ahead. You could also invent a question about limiting reactants. You're more than welcome to do that. None of that is relevant to what the question is asking. Okay? So be careful to only work on the stuff that's being asked of you. If you want to go through and add other stuff, go ahead. But that's not what the question is asking.
Yeah, it's just that I always thought, in your final like that, you just balance the whole thing.
Nope, not necessarily. Right? And why? Because to balance an equation, what do you need to do first? Predict the products.
Which we did.
Make sure the products are correct. So we could give you a question that's balanced the equation. The process of balancing the equation requires now 4 or 5 steps. If you messed up any one of those earlier steps, you might be able to balance the equation, but we're now testing you on content that you didn't know early on. By breaking it down and going simpler questions or shorter questions, we can test at the different levels of what you know within that process. Okay. So if it's going to be just a strictly balance the equation question, we'll probably give you the products so that you can prove that you know how to balance both sides of the equation. yes, officially to balance an equation, you should be able to predict the products first. Okay, and that's how we've talked about it in class.
Are all neutralization reactions double replacement?
All neutralizations are double replacements.
Acid and base produce water?
Acid and base do not necessarily always produce water. I believe that is what our textbook says, which is wrong. But for the sake of this class and anything that I think you would see on the final, it's true, but it's a false statement. It's like teaching kids that atoms have orbitals and there's so many electrons in a sphere around an atom. That's not true. Okay? But it's close enough to true that it doesn't ruin the kid for moving further on in chemistry. Okay? So Bev, you good on that one?
Yes.
Everybody else good with?
Still go ahead and balance it?
Do you want to balance it? Is that what you're saying? Yeah. Let me free up some space in here. So to go through and balance this question, how should you go through and approach this? Once you've got your products correctly predicted, okay, we can now go through and try and balance. Okay. You could start with hydrogen. Arguably, hydrogen's a bad element to start to balance with. You should save hydrogen and oxygen, if it's by itself, for the very end. Okay. So I might start with barium. How many bariums on the left? 1. Bariums on the right? 1. So the barium is okay. Now what do you want to balance? Okay. Nitrate. Are you allowed to balance a complex ion? Yes, so long as it doesn't change. Okay. Nitrate had better show up the same on both sides. I have to have NO3 on both sides. If NO3 becomes NO2, do not balance nitrate because it's changed. Okay. In this case, because it stayed the same, I'm allowed to balance it. How many nitrates on the left? 1 on the right, 2. It's not balanced, so what do I need to do? I need a 2. Because I'm now balancing the equation, I'm changing the coefficient, the number in front of each. That means our nitrate is now 2 on the left. Okay. The next one I would move to would be OH, our hydroxide. Totally meant to do that in black. How many hydroxides on the left? Hydroxides on the right? 1. This is why I like to write it out as HOH. It calls attention to that being hydroxide. Okay. There's only 1 hydroxide on the left. I need 2, so what do I need to do? I put a 2 in front, and this becomes 2. Now I could go through and balance the hydrogens. The hydrogens here could potentially be tricky. Why would they potentially be tricky? Hydrogen shows up in 2 different substances. If I've saved it for last, it ultimately doesn't matter how I go through and balance it, assuming it's balanced at this point. Arguably, what you should do is only focus on the hydrogen that is hydrogen alone. Nitric acid has hydrogen by itself. Right? The hydrogen in barium hydroxide is not hydrogen. That hydrogen is part of hydroxide. And since I balance it as hydroxide, that is not a valid hydrogen. Okay. So how many hydrogens do I have on the left? 2. Hydrogens on the right? Okay. Again, 2. By writing it out as HOH, I can call attention to the differential between hydrogen and hydroxide as not a hydrogen, and the hydrogen in front being it, 2. Okay. This would mean my equation is now balanced. What should I go through and do? Do it again to make sure. Okay. In this case, because you're checking it, you might switch it up, and instead of balancing the complex ions, balance the atoms. Okay. If everything's balanced, it doesn't matter which one I start with. So let's start with hydrogen. How many hydrogens on the left? 2, but I'm switching it up. 4 hydrogens. How many hydrogens on the right? There's 2 from the H plus, there's 2 from the hydroxide, 4. Okay. How many nitrogens on the left? 2 nitrogens on the right? 2. Oxygens on the left. I have 2 with 3, so I've got 6 oxygens from there. I have 2 with the 1. I got 8. Oxygens on the right. 3 with the 2, which gets me 6. 2 with my water gets me 8. What's the last one? Oh, is that it? Oh, barium. Barium's on the left. 1. Barium's on the right. 1. Okay. That method by atom becomes much more difficult, so that might be your secondary check. Okay. It should match, regardless of which method you use, either by complex ions or by atoms, they had better match if the equation is balanced. So if you check both ways and you prove that they're balanced, you should be good to go. Okay? With a test you're crunched for time, I wouldn't recommend testing it a third time. Okay? But ideally you would check it a third, fourth time. Okay? That just depends on how much time you've got left in the test. Make sense? Okay. Are we good with the balancing now?
Yes.
Could you put the phases as well?
Phases becomes kind of a weird borderline. Yes and no. Okay. For a strict predict the products reaction, probably yes. Okay. How would you predict the phases? What is the phase of HOH, also known as H2O? Liquid. Okay. So we know our H2O is a liquid. How about the phase for barium nitrate? How would we know that? Solubility rules. When we go to our solubility rules, there's a rule about nitrates. The rule with nitrates is, it's a nice one because it's an always, no exceptions. Soluble, which means barium nitrate is aqueous. Right. So you could get asked that. That's again one of the pieces of the entire process. Right. It would just be a different, probably sorted out as a separate question because we don't want to test you on everything and potentially oversaturate you.
You know H2O is not a gas.
Really, you should assume liquid. H2O can be a gas, but it has to be hot enough. How would you know the reaction was hot enough? You wouldn't. It's really, unfortunately, what it would come down to. Are we good with what's written up there? I'll actually scan to a different one, just as a quick test. What was the last one we did? 55? Was it 55? No. What was it? Yeah, there. The phase on H2O here is a gas. Why is that one a gas? It's a combustion reaction. You mean explode stuff? Yes. Does that produce liquids? Probably not, because you're exploding stuff, which means lots and lots of heat. The water that's produced will likely be in the gas phase. How would you know that? Chemical experience. Okay. So unless you are actually being tested on your knowledge of chemical reactions, which you aren't, you would just assume liquid.
What's the criteria again for combustion?
Organic, so carbon and hydrogen with oxygen produces CO2 and water. That's it. Does that make sense? Okay, next question. So 53. And what are you asking to solve for? Percent yield. How do we calculate a percent yield? Okay. Our actual over theoretical, okay, times 100. The other way to phrase it would be, okay, you might see experimental. Did I spell that right? Experimental over calculated, or any permutation thereof. Okay? Your theoretical and your calculated have to be calculated. Okay? Sort of. The experimental or the actual is something that you would actually obtain in lab. Okay? So that has to be given to you in a question like this. Okay? You can't calculate it. It literally is an actual yield. Okay? So it's now going back and looking at our numbers and trying to piece together what happened. Okay? So it says starting with 0.657 grams of lead nitrate, the student collects 0.925 grams of precipitate. If the calculated mass is 0.914 grams, what is the percent yield? Okay, so what was the actual yield? Okay. That is our 0.925. Okay. Calculated. Why are you saying 0.914? Didn't I just say it has to be calculated? They told you it's calculated. So yes, it was calculated. It was calculated by somebody else. You just have to use it. Right? So 0.914.
This is probably a bad example. Are we going to have one that is...
Nope. This is the level of difficulty you're expected. Times 100%. Okay? So you're going, well, that's really straightforward and easy. There are three numbers. Okay? If you go through and take a look at your answer choices, those three numbers make up your answer choices, depending on which number you decided to put in the numerator or denominator. So really what this is testing is, do you acknowledge what the actual yield is? Do you acknowledge what the calculated yield is? Can you plug them into an equation to solve? Okay? You might say, well, that's really easy. Throw a third number in there. Take 50 other questions. Okay? After 50 other questions, your brain is starting to feel like goo, and you're going to end up saying, well, I'm just going to jam some numbers in and see what happens. When you jam those numbers in, the odds are you're going to find one of those wrong answers. So you have to know how to solve. The extra wrinkle on this, if we go through and solve this, what do we get for a percent yield? 101%. Can you have over 100% yield? I've got the parts to make 2 bicycles, okay, and I somehow make 3. Does that make sense? No. You don't go into IKEA, buy a box to make a shelf, and end up all of a sudden having 5 shelves. It doesn't work that way. If you've got X parts, you can only make X things. How are you getting above 100% yield? Experimental error. Okay? You're allowed to have a greater than 100% yield. It's not good. It means something was screwed up in your experiment. It could also mean that your calculation was screwed up. Okay? And that's ultimately what this question is now trying to flag on. You come through with a number that's greater than 100. I can't have 100%. I can't take the parts for a table and make 20 tables if I only had enough parts for one. That doesn't make sense to have over 100% yield. I must have done the calculation wrong. So I'm going to pick different numbers. That is exactly what they're relying on here. Trust the method. You have to rely on the method. Does that make sense? Okay. So here's what it is. Yes, it makes sense. That's the answer. Okay. After 50 questions, the answer becomes much less obvious. Okay. So you have to know what you're doing in each of those cases. not to rain on your parade saying that that was easy. All right. Questions on that one? All right. What we did in class, dealing with limiting reagents, doing all those fancy calculations, why did we go through all of that if this is all you're expected to do? Are you expected to be able to do each of those individual conversions? Yes. So ultimately we went through all of those to see what you could do to get to something like this. Look at all of the individual steps and pieces. You're responsible for each of those individual steps and pieces. I just showed you that you could actually use that somewhere, right? But you have to know all of the pieces to get there. Right? So this is another fun one. I haven't actually gone through to check this one or not. I did check it with the percent yield one though. Okay. I see three numbers, 1982, 97.5, and 2.507. 1982. Is that a useful number? No, but I wouldn't be surprised if one of those answer choices involved the use of 1982. Right? So when you read the question, if you see numbers that you're like, that's not useful, cross them out. Right? That way you can at least minimize your possible chances of messing up the calculation. All right, so what do we know? I have a penny equals 2.507 grams. Okay? And I know that 97.5 out of 100, 97.5 is zinc in 100 penny. What are the units on those? Grams. 97.5 grams of zinc in 100 grams of penny. What am I being asked to solve for? I want grams of zinc. In the given information, do I see grams of zinc show up anywhere? Yeah. Where does it show up in my given information? Numerator, denominator? Numerator. Where does grams of zinc need to show up in my answer? Numerator. So what do I need to do? Grams of zinc. Grams of penny. What number goes with grams of zinc? 97.5. What number goes with grams of penny? 100. Why did you not say 2.507? Because that is grams of penny. Okay. The percent is your conversion factor. Okay. Those numbers are tied to each other with those units. You can't just say, well, I'm going to change that number. You've now invalidated that conversion factor. Okay. So by plugging in that conversion factor, I've inserted the unit of grams of penny. Do I want grams of penny in my answer? No. So what has to happen? I need grams of penny in the numerator in front. Okay. Do I know just grams of penny? Yeah, what do I know grams of penny is? 2.507. What's in the denominator? 1. If it's a number other than 1, it's not 2.507. If it's a unit other than no unit, it's not grams of penny. So what do I do? 2.57 times 97.5 divided by 100. There's my answer. Okay. This is one of the big reasons why it's important to take your word question and write the information that you know. Okay? Convert that out into something that you can manipulate. Make sense? That question came from somewhere over here.
Yeah.
You guys good? Okay. You good then?
Yeah.
Okay.
That was super easy.
Okay. Realize, again, 65 questions. If that question is question 65, it's no longer easy. Your brain has gone into mush. You will likely mess that up. Okay? So if you look at it and you're like, I totally know how to do percents now, when you start the test, what should you do? Find a percent question, answer that question right away. That way you don't have to worry about the mush of making a simple calculation mismatch. Okay? So, question 55. Draw the electron dot formula for selenium dioxide and state the type of bonds in one molecule. Okay? So where do we start? This is all the way back in Unit 1. So we're like, we never learned this. Yeah, we did. This was one of those things that I yelled at a whole bunch. Okay? Selenium, this is Lewis structure. How many electrons does selenium have? That was intentionally vague, by the way. How many electrons should I be writing for selenium? Ooh, we got a whole bunch of different answers on that. Okay. Selenium has 34. Okay, but when I do Lewis structure, I'm only concerned about the valence, the outer shell. Where do I find the valence electrons for selenium? It's literally the number in the column. Okay, so that column there is 6. Okay, so valence electrons for selenium is 6. How about for, what's the other one? Oxygen. 6. How many oxygens are there? 2. I total that up, and what do I get? 18. 6 times 3. Okay. Selenium is the least electronegative out of that between oxygen and selenium, so it goes in the middle, and I'll place the oxygen somewhere on the outside. The next step is to put those 18 electrons into the structure. So I'll start with the oxygens, because oxygen is more electronegative than selenium. So there's 8, 10, 12, 14, 16. I need 18 electrons. Where's the last pair of electrons go? Selenium. Anywhere there's a pair of electrons between atoms, I can turn into a line and show up some letters. So there's a line, there's a line. Now what do I do? Our favorite underwater animal. Octet rule. Octopus. I don't know why that's our favorite. Well, it's our favorite because it starts with oct. Okay? We're looking for an octet, so we'd have to go through and check each of those atoms for their octet. If we take a look at the top oxygen, there's 1, 2, 3, 4, 5, 6 non-bonding electrons, and then I have that line. What does that line represent? 2 electrons. Oxygen has access to both of those electrons because it's shared, which means that oxygen has 8 electrons around it. It has its octet. We check the other oxygen, what do we find? Same deal. We check the selenium. It only has 6 electrons around it. Okay? Because it has 6 electrons around it, I need to move electrons towards it. Okay? The common mistake is to erase a pair of electrons and put them on the selenium. The problem there, what happened to our oxygen? Okay? It's now missing. So the rules, if we follow them according to what I've outlined, you need to move that pair of electrons between your atoms, which would mean you have another pair of electrons between the selenium and the oxygen. You now have a second line, because every pair of electrons between atoms is a line. Does the selenium now have 8 electrons? There's 2, 4, 6, 8 electrons. It now has its 8 electrons. We have a valid Lewis structure. Okay? Now we can answer the question. Okay? One line means a single bond. 2 lines means double bond. 3 lines would mean triple bond. Okay? So around the selenium, or actually we don't even need to deal with around the selenium. It just says what are the bonds in this structure? Well, I have a single bond and a double bond. So the first answer, oh wow, yeah, that was kind of silly. Let's look at the last answer. E, 2 double bonds. Do I have 2 double bonds? No. A single bond and a triple bond? Nope. Triple bond shows up twice. Both of those are wrong. 2 single bonds? Nope. There's my answer. Okay. No pressure. I get really mad when you miss this question.
If we were actually drawing them out, though, technically you have to do the second one, right?
If you were asked to draw this out and say, like, I show your work on exam 1 or exam 2, this is not a final correct answer. Okay? Was there more than one pair of electrons I could have moved? Yes. Okay? 2 different oxygens, which means I technically need 2 different drawings. Okay? One as shown, the other one would be this answer, if I draw that out really quickly. You would have to draw both. Okay? It's not asking you to draw them, so you don't need to worry about it. Does that change your answer? No, it's still one single bond, one double bond for either of those structures.
Would it have to be in that shape somehow?
The shape doesn't matter as far as you're concerned. If you move into organic chemistry, then the shape sort of matters, and depending on who you have as a teacher, it may really matter, or they may just be like, you're drawing it crappy. I tend to say you're just drawing it crappy.
Doesn't it have to have like a whole bunch of different angles around it because of our denser or one?
Kind of, yeah. So if we think back to, our fun little thing where you guys made fun of my goofy wrist, right? You're all like, oh, that's stupid. That doesn't make any sense. You can't have your elbows bent like that and then, oh, your wrist is now too long, right? You thought it was stupid. The same thing happens with structures. If you draw out the structures and not the proper formation, you get chemists yelling at you because you drew a stupid-looking structure. The same thing you did to me, I would do right back to you, theoretically and okay. Okay? But even there, we both be like, do you understand what I drew? Yeah? Okay, fine. And I'd say the same thing. I'd still say it looks stupid, but I understand what you're drawing. Okay? Make sense? Okay. Other questions? 56. 56, pretty much the same thing, right? Okay. This one becomes a little bit more challenging. Okay, so we'd start with totaling our electrons. Carbon has how many valence? 4. Yep. Oxygen has 6. Good job counting. There's 3 of them. We also have to deal with the charge, though. The charge says -2. What does that mean happened? It gained 2 electrons. The 4 and the 6 are totaling what? Electrons. So if I've gained 2 electrons, what do I need to do? We'll need to add in 2. What if it said positive? Take away 2 electrons, because we're counting electrons. 24? Carbons are least electronegative. Drop that in the middle. We put our oxygens on the outside. I'll start placing electrons. 2, 4, 6, 8. 2, 4... numbers greater than 2, 4, 6, or 8. How many electrons have I drawn in? 24. That's all I'm allowed to draw in. So now anywhere I have a pair of electrons between atoms, I'll turn into a line. Now I would check octets. What do we see with the carbon? It's missing its octet, so what do I need to do? Shift one of those pairs of electrons in between, making a double bond. Okay? Now when we go through and look at the answers, 3 single bonds. No. 2 single, 1 double. Yeah. 2 single bonds, 1 triple, no. 1 single and 2 double, no. None of the above will be made sense. Okay? Make sense? Okay. Again, that's ultimately a list of rules. Practice those rules and you should be able to get through those faster.
Did you have to put it in the bracket?
Okay. If I wanted to finalize this, you're right, I should throw brackets around that and put in a -2. If I wanted to finalize this, that's still wrong because it's resonance. I had 2 more sources of electrons. I'd have to draw a total of 3 structures. Okay. I didn't have to take the pair of electrons from this oxygen. I could have taken it from this one or this one, which means I need 3 structures for resonance. Okay. It's a bit tight, but we probably have time for one more question if you want to do it.
Okay, I hate to go back to percentage, but could we do another percentage one, because those ones trip me up.
Thing. Okay, we're just looking at different pieces behind it. Okay, because we are a little short on time, we'll go through this fast. It's asking for the percentage of water in borax. So I want grams of water over the grams of borax. Okay. Well, does W show up in the word borax? Are you looking at me weird? No, it doesn't. Okay, so I can't literally just take water and borax. What I'm looking at is what is borax. Borax is that big long formula. What is water? H2O. Okay, so I want to know the grams of water in borax. Well, first off, what is the mass of borax?
Yeah, more mass.
Sodium, I know, has a mass of 20.9. There's 2 of them. Boron has a mass of 10.81. Was there only one? No, times 4. Oxygen, just a 16 flat, times 7. Okay, and we'll look at a second for why I just did it that way. Then I have hydrogen. Hydrogen has a mass of 1.01 times 20. Oxygen has a mass of 16 times 10. Everybody see that?
Yeah.
Okay. I would total that all up, and what do I get the mass of? This is now the grams of borax, and I actually just heard a number. What was it, 300 something?
381.38.
381.38. Okay. Well, what's the mass of water?
180.2.
The mass of water is right here. Okay. Not 18, not just H2O, but there's 10 H2Os there. Okay. So I would have to total that up to get my 180. And change, right? What was the number? 180.2 grams of water. I now go through and run the calculation, and I always forget it, times 100%. And that's where we'd have our answer. 49 is doing the same thing, except I think you're looking at platinum in that compound.
Yeah.
So you would take grams of platinum divided by the mass of everything, including the platinum. Okay?
Just as a, like, something we should do every single time we see a question that asks us for a percentage of something, and we just write 100.
Yeah. If you're asked for a percentage, you should always do the multiply by 100. It's become so ingrained in me that I never write the 100. I've internalized that I have to multiply by 100.